Now, we have another example here in front of us in which we have to tell about the stability of carbocation in the following species. So we have the first, the second, and the third species in front of us, and we have to tell the order of stability in these species. Now, you can see that each one of them is similar in that sense that they all have benzene, and also they all have an OH group attached to them and a CH2 positive, that is a carbocation. So all of them are actually same, but they only differ in the positioning of the OH. So let us begin. Now what we notice first is that we have OH group, and OH, in OH we have O, which is an electronegative atom, and we have been doing this for quite a while now, that if we have an electron negative atom, that group starts acting as an electron withdrawing group. So this group starts acting as an electron withdrawing group, and it will start showing minus I effect. So the first effect that we can see in the above examples is that they all have minus I effect because they all have OH, and you can see that they all have OH. So each of them will have minus I effect. Now let us just mark saying that each one of have minus I effect, the second case and in the third case. So we have minus I effect in each of them. Now what happens is, when we have minus I effect, they'll start pulling the electrons, of course. So we move on to the next effect that we'll be seeing. Now OH group, again, we know that OH has a lone pair of electron. So it possesses a lone pair of electron. Now, when it possesses a lone pair of electron, what happens is, we know that it will start showing, what we have been doing is that it will start showing plus M effect, and OH will start behaving like a plus M group, because we have been studying that any group which possesses a lone pair of electron will start behaving like a plus M group. Now we can mark again that OH will behave like a plus M group too. So we have plus M effect also. Now notice that I have not written plus M effect in the second case of this example. So why is that? Because we can see that if I take an example of a carbocation that we have been doing, so if I take an example of a carbocation, and we see this one thing, that if I have a carbocation here, when this positive charge is possessed, pi bonds start shifting their electron density, and what happens is we get a new resonating structure, and the positive charge is shifted here. So we have two double bond here, and then we have CH2, and of course the rest of the bonds remain intact in their places. Now what happens is, this plus I will also start affecting the next group attached to it, and we again have a resonating structure where the plus positive charge is now here on this position, and the double bond is shifted, and we have this. Now notice, if this charge keeps on going forward, what happens is that we get positive charge on two spaces. On two positions, we have got positive charge. So we have positive charge here now. Now, as you can notice that the positive charge is coming on this position, it is also coming on this position, and it is coming on this position. So notice that we have got three positions where we are having the positive charge. This one, as well as this one. The two on the upper hand have the same position, and this position is called the ortho position. So we have the ortho position here, and we have the positive charge at ortho. And this position here called para, we have the positive charge here also. So resonance is limited to ortho and para position. Okay, so two positions we have resonance effect, that is ortho and para position. Now, in the previous slide, we have seen that OH is here. So in the second one, this OH here will never get a positive charge because it is at meta position, and meta position does not participate in resonance. So we cannot assign a plus M charge to this one, a plus M effect to this case. Okay. Now, so the carbocation only goes to the ortho and para position in the resonance structure. So we can say that the carbocation only goes to the ortho and the para position. Now, next up, we have to compare these three, the first, the second, and the third one. So let us begin comparing them. Now, what I see is that each of them, the first and the third one, has an extra effect, the plus M effect. But we have the minus I effect too. So the plus, we can leave this, the second one. The second one is the least stable, of course, because it has the minus I effect, and minus I means it is electron withdrawing in nature, electron withdrawing group. So it is withdrawing the electrons. And when we know that the positive charge in any carbocation, if there is an electron withdrawing group, it destabilizes. This is destabilized. And what happens is, when it is destabilized, of course, this goes to the last position. So second is last. Now we are having a competition between the first and the third one. The first and the third one are greater than the second one. So now we have to compare between the first and the third. Now the first and the third differ only in the case of minus I, because minus M has the same effect wherever we put it, because resonance is a phenomena which travels throughout the body of the species. So we have resonance in the whole species. So we cannot classify them on the basis of resonance or the plus M effect. But then again, we have the minus I effect, which will help us in distinguishing between these two. Now, what minus I effect does is, we know that minus I effect, it depends on distance. Minus I effect depends on distance. Okay. So what happens here is, this is another point that I am discussing. So minus I effect is depending upon distance, and it decreases with distance, and it decreases with distance. So the nearer the minus I effect, the more is its effect on the species. And thus, if the minus I effect is near to the carbocation, which is apparent in the first case, you can see that the minus I effect is nearer to the carbocation, so it is gonna show more minus effect. So we can just say that this will have more minus effect and this will have less minus effect. So what this does is OH is showing more minus effect in case 1. More the minus effect, the more is the electron withdrawing nature and the more is the destabilization. So we can just see that the first one is more destabilized than the third one. So which one from the first and the third gets a superiority in the stability series? It's the third one which wins the race, followed by first one and the second one. So if I want to compare the electron delocalization as well as the stability of the carbocation, so 3 wins the race, and 3 is the most stable out of all of them because it has less minus I effect, so less electron withdrawing. It is causing less destabilization in this carbocation here, and thus leading to more stability in the species. So we have 3 is greater than 1 is greater than 2. That was the answer to the question. So let us just finish by writing that this was the answer that we wanted and we have explained in the whole till now. Okay.